Welcome to this Concept Explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we're going to take a deep dive into the concept of dielectrics and polarization from Unit 2, electrostatic potential and capacitance. And we'll make sure you understand this crucial scoring concept clearly and securely for your board exams. Okay, let's unpack this with a simple everyday question. You've probably done this. Why does a plastic comb, after you run it through your dry hair, attract and pick up tiny pieces of paper?
Oh yeah, that's a classic experiment we all do. But wait, I've always wondered about that. The paper is an insulator, isn't it? It can't conduct electricity or allow charge to flow. So why does it react at all? I thought insulators just, block everything.
That is precisely the core confusion we need to clear up today. See, the paper is not a conductor, you're right, but it is a dielectric. And the charged comb, it polarizes the paper. This simple trick is actually fundamental to modern electrical engineering.
It proves that even if charge cannot flow through a material, the material can still react to a field.
Exactly. It can still react. Now, can you think of another real-world example where this distinction matters greatly? It can even be a life or death thing.
I'm not sure. Something surprising.
Think about the massive rubber tires used on aircraft. Now, ordinary rubber is an excellent insulator, but aircraft tires are manufactured to be slightly conducting, not perfectly insulating.
Why would they do that?
It's so that any static charge built up from friction during the flight can be immediately conducted to the ground when they land.
Ah, I see. If the tires were perfect insulators, the charge would build up and whoa, the first person to touch the plane could get a severe shock or even cause a spark, which is dangerous with fuel around.
Absolutely right. So a conductor grounds the charge while a pure insulator or a dielectric holds onto it. And that can cause attraction through this thing we call polarization. So let's get into the core idea. Dielectrics are non-conducting substances. What this means is they have basically no free charge carriers. Unlike in conductor, where free electrons rush to the surface and just completely cancel the external electric field, dielectrics can't do this. Their charges are bound tightly within the atom.
So they're insulators, but they're still affected by the electric field, just in a more restricted way.
Precisely. To visualize this, let's use the stripped classroom analogy. In a conductor, the students, who are like the electrons, are free to change seats. They can rush to one side of the room to cancel out a disruptive force. But in a dielectric, students are, let's say, tied to their desks. The desks are the atoms.
Okay, so they can't move around freely.
They can't. They want to move, but they can only lean. They can only polarize. This leaning, it creates a small opposing tension inside the material. But because they are bound, they can't completely eliminate the external force. They only manage to reduce it.
I like that analogy. The leaning creates an opposing force. But what's the practical purpose of this? I mean, why do engineers actually care about this atomic stretching?
That's the why it matters part. This property allows engineers to store far more energy and to miniaturize electronics dramatically. Think about it. Air is a very poor dielectric. Its K value is almost 1. If you wanted to store a certain amount of energy using an air capacitor, you might need a huge room-sized device.
Okay.
But if you use specialized ceramic materials, which can have a dielectric constant K value close to 1,000, you can get the same energy storage in a tiny chip, the kind you find in your phone. The dielectric material itself does most of the field-reducing work.
So it's all about maximizing storage while minimizing size. That makes sense.
Exactly. Now let's build a mental image of what's happening inside. Visualize the atoms as perfect neutral spheres. When the external electric field hits, the positive nucleus shifts slightly one way, and the negative electron cloud shifts the opposite way.
So the sphere becomes distorted.
Yes, it turns into a slightly stretched oval or an egg shape. The whole material now looks like a stack of tiny electric dipoles, all aligned in one direction. This partial alignment is what generates that small internal electric field that fights the external one.
So it's an induced surface charge, not a free charge that flowed from somewhere else.
That is the crucial distinction. You've got it. It's induced. Now, let us see how NSERT defines this concept formally. We should focus on the key words you'll need for the exam.
All right, we'll read the formal definition from the source text. Dielectrics are non-conducting substances. They have no or negligible number of charge carriers. The external field induces dipole moment by stretching or reorienting molecules of the dielectric. The collective effect is net charges on the surface of the dielectric, which produce a field that opposes the external field. Unlike in a conductor, however, the opposing field so induced does not exactly cancel the external field. It only reduces it.
That's a dense but critical definition. Let's pause on one phrase, the induced dipole moment. This is the key to understanding the two types of molecules in dielectrics. It's a very common 3-mark question.
Oh, wait. There are different ways molecules polarize. I thought all atoms just stretch.
Ah, that's the mistake students often make. They stretch in one type, but they rotate in the other. First, consider nonpolar molecules like oxygen O2 or hydrogen H2. They're perfectly symmetrical. The centers of positive and negative charge coincide, so their normal dipole moment is 0.
Okay, so they're perfectly balanced to start with.
Correct. But when the external field, let's call it E0, is applied, the positive and negative centers are forced apart. The atom physically stretches. This creates a new temporary or induced dipole moment.
I see. So for nonpolar molecules, the field literally creates the dipole by stretching the structure. What about the other type?
The second case is polar molecules. Think of water, H2O, or HCl. These molecules already have a permanent dipole moment because their charge centers are naturally separated. They are already like tiny magnets.
But if they're randomly oriented, the net effect is 0, right?
Exactly. In the absence of an external field, thermal energy makes them point in all random directions. The net dipole moment of the whole material is 0. But when that external field E0 is applied, the individual dipoles tend to align themselves. They rotate to line up with the field.
So they aren't stretching so much as they are rotating into formation.
Precisely. So to summarize, nonpolar molecules stretch to create a dipole, and polar molecules rotate and align their existing dipoles. But the final result is the same. The whole dielectrics lab now shows polarization. It develops these net charges, plus minus sigma p, only on the surfaces. And this creates an opposing internal field, EP. So the final field inside is always reduced. E equals E0 minus EP.
Okay, that distinction's much clearer now.
Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. Now, let's quantify this reduction using the dielectric constant, which we denote by K. The dielectric constant K is defined as the ratio of the external field E0 to the net field E inside. So K equals E0 divided by E.
Since the net field E is always less than the external field E0, does that mean K must always be greater than 1?
Absolutely. For a vacuum, K is exactly 1. For any material dielectric, K is always greater than 1. This constant, K, tells us exactly how much the electric field is weakened inside that specific material. Let's do a quick worked example. If the external field E0 is, say, 100 units, and you insert a piece of glass which has a dielectric constant of about K equals 5.
Then the net electric field inside E net would be 100 divided by 5, which is 20 units.
Correct. The glass has cut the field strength by 80%. The larger the K value, the weaker the final field inside becomes. Now let's connect this to the next big topic, capacitance. This is where it all comes together for engineering.
Okay, so if we put a dielectric slab into a capacitor, the field E between the plates is reduced by K. That's clear. E becomes E divided by K.
Excellent. Now what about the potential difference V? Remember the relation V equals E times D, where D is the distance.
So if E is reduced by K and the distance D is fixed, then the potential difference V must also be reduced by the same factor. KV becomes V divided by K.
Precisely. This reduction in potential is the key. Now, what's the fundamental definition of capacitance? C equals
Q by V, where Q is the charge on the plates.
Right. And we assume Q stays constant when we insert the dielectric. So if Q is fixed and the potential V in the denominator drops, what happens to the capacitance C?
If the denominator gets smaller, the capacitance C must increase to compensate.
Exactly. If V drops by a factor K, then C must increase by a factor K. Thus, the new capacitance is C new equals K times C original. Dielectrics are put into capacitors specifically to boost their storage capacity.
So the goal isn't just to reduce the field, it's to use that reduction to lower the voltage needed for a certain charge, which then massively increases the storage capacity. Wow, that link is so clear now.
Good. Now that the concept is clear, let's talk about the silent killers, the small misconceptions that cost marks in the exam.
Okay.
Misconception 1. This is the most common one. Students confuse dielectric constant K with conductivity. They wrongly assume that a material with a high K value, like that ceramic with K equals 1,000, is somehow a better conductor.
So they think high K means high conduction. That's wrong.
Absolutely wrong. That's the mistake that sinks scores. The correct idea: high K means the material is highly polarizable. It stretches or aligns very well, but is still an excellent insulator. Remember the aircraft tire. Rubber blocks current. It's an insulator, but it's a good dielectric. Don't mix up flow and stretching.
Right. High K means high stretching power, not high conducting power. Got it.
Well,
What's the second silent killer?
misconception 2. Some students remember that the field inside a conductor is 0, E equals 0. And since a dielectric reduces the field, they jump to the conclusion that the potential inside a dielectric must also be 0.
But the field is only reduced, not 0. So the potential can't be 0 either, right?
You got it. It is reduced, but it is definitely not 0. The correct idea. The field E is reduced to E0 by K. It's only 0 in an ideal conductor. In a dielectric, the potential difference V is reduced by K, but V itself is non-zero. Remember, for a conductor, E is 0 and V is constant. For a dielectric, E is reduced and V is reduced. Neither are 0.
That distinction is so important for theory questions. Reduced field means reduced potential, not 0 potential.
Exactly. Okay, to make sure these ideas stick for the exam, let's use some easy memory anchors.
Right.
First, to remember the effect on the electric field, use this phrase: dielectrics die the field. They kill, or at least significantly reduce, the electric field strength.
Dielectrics die the field. Simple. I like it.
Next, for capacitance. Remember the mnemonic K is king. Since the formula is C equals K times C naught, the dielectric constant K always makes the capacitance C bigger. K is the king that boosts the value.
K is king. Okay.
And finally, let's try a physical gesture. The stretch, don't flow gesture. Hold your hands together flat. That's the atom with charge centers coinciding. Now, when the field is applied, slowly pull your hands apart just a little bit, keeping them parallel.
Ah, I see. My hands moved apart slightly, but nothing slowed away. It just shows that internal stretching. That makes the difference between polarization and conduction so clear.
Perfect. That visualization confirms it. Now let's quickly summarize the 3 key facts about dielectrics and polarization for your revision. First, dielectrics are insulators that undergo polarization, that's internal stretching or dipole alignment, in an external field. Second, this creates an internal opposing field, reducing the net electric field inside. The net field is always E equals E0 divided by K. And third, because the potential difference reduces, inserting a dielectric always increases the capacitance of a device by the factor K. So C equals K times C naught. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is PROF Sam.
Yes, ProfSam.com. Thank you for joining this deep dive. Study well.